The second part of this lecture, and the main thing here, is about series. Now, series, you remember for 131A, you can think of it as, say, geometric series. You can represent as a sum of triangles here. You have a square of side length 2. Then if you split this triangle in this fashion, so first divide it by half, and then at every stage divide what remains by half, then what you get is, well, half of the area 2 is 1, then half of what remains is 1/2, 1/4, 1/8, 1/16, etc. And series is about summing up these things cumulatively and analyzing when things converge. I mean, this was at least summing up real values. In this case, this picture, what it's representing is sum of 1/2 to the n, when n is going from 0 to infinity, and it's showing that this sum is equal to 2. Because the area of these combined triangles is exactly the sum of its pieces, and this is the infinite sum. Now, the change in this class is that we have functions here. You could think we saw a similar hierarchy earlier, that, in 131A, you start from limits of sequences, then you go to series of numbers. Well, now last week we talked about limit of a sequence of functions, so natural next step is a series of functions, limit of a series of functions. So it similarly to how from sequences you go to series, sequences of functions you go to series of functions, and that's the type of theorems that you also see applied. So how did we define limit of a series converging in 131A? Well, a series in 131A converged if the sequence of partial sums converged. And the same thing works here in the function spaces as well. So if you have a sequence of functions, we say that the series, that is the sum of these functions, converges, and you can say either pointwise or uniformly. So these are exclusive. Everything applying to uniformly is in red, pointwise in black. If the sequence of partial sums, so you sum only up to an index n, now this is a particular function. If this sequence of partial sums converges pointwise or convert respectively uniformly to some function s of x, then this is said to be, we say that this series converges. Any questions on this? We'll see some examples. And one particular one is this. There was some campus wire. This is clearly explained what you can say. So if you have x to the n, I mean, eventually one of the things we will discuss is Taylor series, and power series. So this makes already sense to start from that. Now the series x to the n converges pointwise on -1, 1. We all know this, to 1 minus 1 over x. 1 minus 1, 1 over 1 minus x. Sorry. It converges pointwise. This is, but not uniformly on the full interval. But if you take some part of this interval, you actually do get pointwise or uniform convergence. So you have -1, 1. This smaller interval here is some compact thing contained in it. This compactness plays a role in this part. But there was a nice proof of this fact on Campus Wire. So feel free to look at that. It was one of the 2 math questions posted there. I don't want to, if you are interested in that discussion carefully, look at one there. Okay, so it's basically one way of thinking about these series is that it is just like 131A, but you have a variable here that you can plug in different values. So in this case, if you plug in a value between -1 and 1, you do get convergence to this 1 over 1 minus x. And you get that the convergence rate does not depend on x as long as you avoid the endpoints here. Now, we want to prove that series converge. We want to analyze series, a variety type of series, Fourier series, Taylor series. And the basic question, just like in 131A, and you can be sure to see a question like this in the homework, probably some form of question like this on the final, is how do you prove that a series converges? I mean, that's the basic thing. You've defined a concept. How do you prove that that concept actually makes sense in a particular case? Well, I mean, before you talk about series of functions, you have to understand how do you prove a series converges in 131A? Because the tools that we will use are basically just refinements of the tools that we had in 131A. And okay, there are a million different tests that you could apply, but essentially there are only two tests. Everything else is kind of refinement or variant of these two tests. So there is absolute convergence test and there is comparison test. So, I mean, this is crudely, you might want to apply other tests, but so what does absolute convergence test? Well, it says that if you take the series of absolute values of some numbers, if the series of absolute values converges, i.e., I mean, this is a positive series, so the sequence of partial sums is increasing. So it has only two possibilities, either infinity or finite. So convergence means exactly that this infinite sum is finite. So if it converges, then the sequence without the absolute values converges. So absolutely convergence implies conditionally convergence, and you know the examples that you don't have the converse. So an example of this would be that sum of sine n over n squared converges, because if you take the absolute values, you can bound by 1 over n squared. Okay. And you can think that this an should now be kind of our fn of x. But let's not introduce the x quite yet. Okay, so absolute value thing. But already this example says that, like I mentioned, you compare it to 1 over n squared. So usually these arguments are always combined with some simple estimates from above. And one way of stating that is that if you have an less than or equal to bn, and the bn converges, then sum of an converges. So this is one way of stating a comparison test. If you make the absolute values bigger, then you get something convergent. And these are proven how? By showing that the sequence of partial sums is actually a Cauchy sequence. Crucial tool here in these proofs was Cauchy. And it will play a role again. But I won't go over that proof now. You can look at, say, Kenneth Ross's book if you want to see a proof of that.
So when you say that these are the only two methods we use, don't both of these methods rely on previous knowledge of other convergence sequences? So like the example you gave relies on knowledge of the convergence of 1 over n squared. So would that suggest that you could also just directly prove that something converges? Like, for example, with like 1 over n squared, you could use like induction to just show that there's a limit to it. And then you're like, you know what I'm saying?
Yes, yeah, I understand. Yeah, that is a good point. So this is a bit simplifying. I mean, in addition to these, there are some known. Essentially, there are two types of series that we know converge. Additionally, this p-test. Well, actually, I would say additionally geometric series. This converges if A is in -1, 1, it converges, otherwise diverges. So, I mean, in this, what I will say in that case is that there are kind of, so in this case, why do we know this? for a geometric series, we know the formula for this. So we know the sequence of partial sums exactly. So if you sum up a to the n, you know that this is exactly whatever a to the, well, yeah, put 0 there. So then it's, I believe, a to the 1 minus a to the n plus 1 over 1 minus a. If I did this right. So there's a formula for this, and you can look at what happens when n goes off to infinity. This is an excellent question. So it's for geometric series, it's kind of a coincidence that you're able to analyze the convergence because you know the exact sequence of partial sums. So that's why, okay, we compare a lot of things to geometric series. But not, yeah, good point. I said about 1 over n squared. What was that based on? And this, so sometimes this is called the p-test, but behind there, that is also some sort of idea of comparison. But it's one has to think more about what to compare to. So one can't use induction because, well, at least not a trivial induction, because it's not clear what the upper bound is that would depend on n. But what you do is you look at the partial sums. So you look at the partial sums and you estimate them from above by integrals. So if you look at x to the minus p, so 1 over x to the p, and you look at these terms, 1 over n to the p, then you can find them as, well, we want an upper bound because we want to make it converge. Most of these terms, we start from 1, 2, 3, they can be found by drawing these rectangles under the graph. I mean, this is 1/2 to the p, that's 1 over 3 to the p, etc. So one can prove with a little work that this is less than or equal to 1. Well, the first term is not in this picture, plus the remaining terms, which can be estimated from above by the area under the graph, 1 over x to the p. And that gives you a bound for this increasing sequence. So yes, it's a little simplistic. That's an excellent question, and it's good to clarify this, that in addition to these, we need to know something about geometric series and p-test. But even then, the idea is then based on either directly arguing what the formula is or estimating from above. So kind of comparison to an integral in that case. But that's a good point. Very good point.
All right, thanks.
Yeah. Other questions? Yeah. So yeah, we will need regularly that geometric series converge and this the p-test. We will need these. I mean, kind of this discussion about absolute convergence and comparison, I mean, it's just deferring the question to something else converging. So we have to have some large enough set of things that we know converges, a library of things. Okay, excellent. That's good that we got to review those things as well. So what about functions? Actually, since we've been pretty good with our time, I want to add one example here that was in our homework. I think it was homework number 1. This is a bit similar to this example. So in homework number 1, you were asked to prove the following. Suppose Vn are vectors in Rd. You have a sequence of vectors in Rd. And the norms of Vn are summable, so it's kind of absolutely summable. Then you proved a sequence of things. You proved that the sequence of partial sums, let's call these W, capital N, Vn, these are Cauchy, and therefore the sequence of partial sums converges. as RD is complete. And therefore, we can talk about the infinite series of these vectors, and we can say analogously that this series of vectors converges. So again, here, what plays a role is absolute convergence and bounds for absolute values. Okay, my battery is dying, so I have to adjust my position a little bit. So you want to keep this in mind. The idea is to bound by absolute values. And you also want to keep in mind that you did similar estimates. The proof scheme is kind of the same for functions. We will start from some absolute values kind of converging. We'll prove that something is Cauchy, and then we'll use completeness to argue that limits exist. So the scheme is always the same. Now, okay, how does this look like for functions? We have to do some modifications. So this is called the Weierstrass M-test. M because there's this M in the proof. So let's suppose we have some functions on a metric space that are real valued. Series only makes sense for real valued or at least vector valued functions. And these are functions, they don't have to be continuous, but it doesn't hurt to assume that they are continuous. It doesn't really help you either. Okay, and these are functions that are bounded, but each of them is bounded by a different bound. So there exists an Mn, so that for all x in the space, Fnx is bounded from above in absolute value by Mn. And we have this, where it comes from, it's kind of a replacement for this absolute value of the function. We want to have a bound that doesn't depend on x, and which we can reduce to 131a, and that's why we make it a uniform bound. So we have some bounded functions where the bound is Mn, and then if the series of these real numbers Mn converges, then the sequence of functions converges uniformly. The series of functions converges uniformly. So kind of absolute convergence, or some version of absolute convergence, means that the series converges. This is and uniformly. Any questions on the statement? We'll see applications of this at the end. But since we have the proof scheme fresh in our mind, let's go through the proof. So again, always a proof has a setup. Suppose we have some functions. Suppose we have the bounds that we stated. And suppose that the series converges. Now we want to say that the series of partial sums converges. Now, logically, it makes sense first to talk about pointwise convergence. So let's first fix an x in x in order to establish pointwise convergence. Of partial sums. So S capital Nx equals, and I want to put a different index here because we'll need the capital N for the Cauchy condition. So S little nx is sum, and I'll change the index of summation to I just so that I can use the N on top. Okay, so we have this sequence of partial sums. Now, how do we show that something converges? Well, again, we show that it's Cauchy. The reason we show that it's Cauchy is that we have no idea what it's converging to. So we can't really just say that we can't say anything else. Now, it's really important to notice that these are real numbers now. X is fixed. We're looking at a pointwise thing. This is a real value, just the 131A series. Well, actually, we don't need the Cauchy condition here. Let's go more directly. So how do we get that this converges? Well, we said that we essentially have two tools that in 131A help. So this is a series of real numbers, AI. So it's enough to show that it converges absolutely. Well, actually, I'm going to go more direct because we stated the comparison test in this way. Now, and now I want to introduce this AI so that I forget about the X for a moment. This depends on X, but I don't want to emphasize the dependence because X is fixed. So absolute value of AI is equal to absolute value of FIX is less than or equal to MI by assumption. And sum of MI equals 1 to infinity converges. The series of the real numbers MI converges. Therefore, by the comparison test we stated, so since this is true, and that converges, the series sum I equals 1 to infinity, AI converges to something. So this is using 131A, the comparison test as we did. Okay, so now we have a conversion thing. This series is converging for a fixed X. So because it's converging, we can define a limit function. Let's use I still here as an index. So fx equals sum I equals 1 to infinity fix. Conceptually, this is an important step because if you're proving convergence to something, somehow you should establish that the limit exists or limit is something. So what we're doing here is we're finding the limit pointwise. And then we're generalizing it to all X. So this defines a function f x to r. Okay, now what remains is that we have to show that this sequence is converging uniformly to it. So we fixed an X here, we got that we get converged to some function f of x that we define. Basically, we forced this to happen. And all we had to do was we had to check that this series of partial real numbers converged, sort of for a fixed X. But then we have to worry about uniform convergence of this function. And this requires a little bit different analysis. So let's look at, well, we want to prove uniform convergence. So fix an epsilon positive. We want to estimate for all X in the space, the difference between the partial sum and f of x. And we would like this to be less than or equal to epsilon. But okay, how do we get there? Okay, so now useful to think of this X as fixed. So now what do we have here? We have the sum of real valued series. And if you find this X confusing, think of them in your mind as AI. But I won't write it now like that. So fi of x, that's a real number. It depends on x, but it's still a real number. And you have the sum up till n minus the sum I equals 1 to infinity fi of x. Okay, so what is common, and this is an estimate you often use with series. So if you have a sum up to n and sum up to infinity, So what is left after you take the difference is the terms I equals n plus 1 to infinity fi of x. More space here. Then, okay, this is the sum of real numbers. So by triangle inequality, this is true also for infinite series. We can pull the absolute values inside. But now each of these fix is less than or equal to m of n. So the sum of positive numbers is less than or equal to sum of mi. And this is equal to the infinite sum of mi's minus the finite sum. I'll just move this formula. So this is equal to the infinite sum of mi's minus the finite sum. And why I write this like this is the limit of the series minus the partial sum of the series. The partial sums are converging of mi, so I can make this difference small if n is bigger than or equal to n. And where does the choice come from? So let's make this rigorous. Since limit as n goes to infinity of partial sum of mi's is equal to the infinite sum of mi's, there exists an n such that if n is bigger than or equal to capital N, then the difference between these, and this is bigger than that because you're summing in more terms, is less than or equal to epsilon. So you don't, I mean, technically absolute values, but because it's positive, you don't have to put the absolute values. So with the same n, if n is bigger than or equal to n, then what we get is, for all x, the difference between the sum, the infinite sum, is equal to the sum of the tail. So sometimes this is called the tail because you only have terms after then a certain index. You pull the absolute values inside, you do the obvious upper bound, but then you get a difference of mi's, and you argue that the limit exists. Now, by the choice of n bigger than n, this difference here is less than epsilon, and we're done. And we got uniform convergence here. Why? Because the capital N does not depend on x. It only depended on the mi's, which did not depend on x. They were uniform in x. So we're done. Questions? What do you think? If you have questions, I just want to clarify one thing here in this proof. So this step here, you could also do by proving that this sequence of partial sums is Cauchy, and you could do that by estimating the difference, Sn minus Sm. And what you would get is a difference of mi's. But that difference of the sum of mi's, this can be made small because it involves a convergent series of partial sums. And that's another way of going about it. And then you would use completeness of R to argue convergence. But this time we can just use the comparison test from 131a to speed this up. Okay, so this is a bit technical, certainly, but let's say some corollaries and examples. You don't have to understand the proof at first. I think you have to read it and think about it to understand it better as well. So, okay, if these functions are additionally assumed to be continuous, and if you have the same bound, then as a corollary, you immediately get that the infinite sum is actually continuous. Why? Because it's converging uniformly. So by Weierstrass M-test, the sequence of partial sums converges uniformly to the infinite sum, and the sum is continuous. Each of these partial sums is continuous, so you're good. Continuous, and then a uniform limit of continuous functions is continuous. By theorem again. So uniform limit of continuous functions is continuous.